Good afternoon. I'm Anna Willett. I work for SETCO Minerals Technologies Incorporated, and I'm going to talk about the versatility of surface modified clay adsorbents for PFAS treatment. It's over here. So just to start out, Fluorosorb is the trade name of the product that SETCO manufactures. The company owns the mines that where the bentonite clay that's used for Fluorosorb is mined, and then has a manufacturing facility in Aberdeen, Mississippi, where Fluorosorb is manufactured. We refer to Fluorosorb as a surface modified clay, and I'm going to talk to you about what surface modified clay is because many people wonder what it is. The product has been, it's an adsorbent for removal of PFAS from water or stabilization of PFAS in soil. It's been commercially available since May 2019. It is certified for drinking water use by NSF 61. And I'm going to present some of the test results that we've generated with university partners and also through some field piloting. To start, Fluorosorb is very versatile in its deployment, and that comes primarily from the ability to manufacture the product in different grain sizes, which are shown here. The D50 that you see listed at the top for each little pile is the median diameter. So the smallest product is Fluorosorb 100, and that is being used for soil stabilization and solidification. So stabilization, if you just want to stabilize PFAS and reduce PFAS leaching in soils, and solidification, it can be mixed with Portland cement. I'll show some results if I have time. It's my very last slide. Fluorosorb 200 is the middle grade product. It's actually the most widely used. It can be used as a permeable reactive barrier where trenched into the subsurface, it acts as a barrier treating PFAS that would be flowing through the ground as groundwater through the PRB, and PFAS is absorbed to the Fluorosorb with the effluent being clean groundwater, very similar to a traditional PRB of other substances, but specific for PFAS. It can also be used in water wastewater filtration in filtration vessels shown here. And I'll present most of the results we have are from filtration vessels. And finally, really unique product, it can be made into something called a reactive core mat or an RCM. It's it's basically Fluorosorb sandwiched between two permeable geotextiles. Comes in these rolls that are shown here. They can be rolled out and layered upon contaminated sediment, for example, where it acts as a very thin sediment cap, so we would reduce PFAS leaching from the sediment into the waterway above. The Fluorosorb absorbs the PFAS and the water passes through the RCM. Whoops, what happened to me? Hold on, my arrows are not working. Let's go back. Let's advance it here. Okay, so what is surface modified clay? Surface modified clay absorbents are obtained by converting sodium bentonite to an adsorption media using a modification agent that has a high affinity for a variety of PFAS. And basically that's what this picture here shows. So clay is these platelets or sheets of alumina and silica hydroxide with cations and water in between, and that gives the property that most people know about bentonite clay, which is that it swells when you put it in water, because water comes into these intergallery spaces and the clay swells. When we react the modification agent shown here with the clay, it replaces the cations and water in the intergallery space and makes the clay basically hydrophobic so that it does not swell when contacted with water. And this is a phenomena that can be tracked by something called the despacing, which is measured in the laboratory with an X-ray diffraction scan. It's a pretty basic measurement. The despacing for bentonite clay is 10 to 13 angstroms. And when you have the surface modification, the despacing rate increases to 15 to 35 angstroms. The modification agent is specific for PFAS in that it has a positively charged head group that will attract the negatively charged head groups of negatively charged PFAS, which most are that are of regulatory concern. And then it has a hydrophobic hydrocarbon chain that is a driving force for absorption for the perfluorinated chain of PFAS compounds. So it has a dual driving force in terms of absorption of PFAS, and it's more energetically favorable for the PFAS to partition into the adsorbent and associate with the surface modification than it is to stay in the water or soil. I'm sorry, in the water. And this leads to a unique absorption mechanism, which is shown here. This is another cartoon kind of showing this the same thing, the despacing increase, but increasing of the clay, but this is just as the PFAS sorbs in the intergallery spaces. So basically, this is a plot of absorption capacity versus equilibrium concentration. And as the concentration, the starting concentration increases, you get the step change in absorption capacity. So you're getting more PFAS in per gram of Fluorosorb. And that's because, and this has been verified with modeling and also looking at the despacing in the laboratory, was published in Water Research in the last couple of years. So the despacing also increases as various PFAS molecules sorb to the surface modification in the clay. And here's the actual data just showing that step change. So we see this with every single PFAS compound that's been tested, which is a good, 18 or so different compounds have been tested in the laboratory. So I guess the conclusion is that this is not a surface area modify or surface area driven mechanism like you would get with granular activated carbon or GAC. It's a unique property in that the area available, the reactive area of the surface modified clay actually increases as you increase the PFAS concentration. This is some basic lab studies done at McGill University. These are batch studies with an contaminated groundwater from an AFFF training area mixed with Fluorosorb and incubated. This is at equilibrium, and it's showing that Fluorosorb will absorb the long chain PFAS very well. Performance, it still does absorb short chain PFAS like PFPEA, but the percentage is reduced, and same with FOSA, which is another, or I'm sorry, FBSA, with another 4 carbon shorter chain PFAS. And that was also shown in the same study. They made a plot of the KD or linear distribution coefficient, which is a measure of absorption capacity, and the molecular weight for the different classes of PFAS, so carboxylates, sulfonamides, sulfonates, and fluorotelomere sulfonates. And you can see that as chain lengths, well, first of all, sulfonates are the best absorbed, fluorotelomere sulfonates the worst, if you can put it that way. But as the chain length increases from C4 to C8, so this is PFOS up here, the highest absorption capacity basically on Fluorosorb, the absorption capacity increases significantly. But you can see that PFOS and PFOA have have higher absorption capacities when looking at the suite of PFAS compounds. So getting right into some testing, Orange County Water District has a PFAS testing program for the PFAS in their groundwater. And I'm going to talk about, as quickly as I can, the pilot study. And they also did something called rapid small scale column test, which is where you grind media, put it in a tiny column, and then you're able to get breakthrough quicker because the media takes a long time to break through. And this, for example, this pilot study took 18 months to get data. So they have low concentrations in their groundwater. And they did a pilot study comparing all these medias, started in December 2020, ended October 2020, or I guess it was started earlier than, it started in 2020, ended October 2021. And the Fluorosorb results are shown here, highlighted in orange. Fluors for PFOA, right here at the top, Fluorosorb lasted the longest. So the way you read this is that the concentration is on the y-axis and time to breakthrough is on the x-axis. And the longer time to breakthrough means more water was treated before you hit your treatment target, which in this case is the California notification level of 10 nanograms per liter for PFOA. So you can see that all the other media broke through to that red line prior to Fluorosorb, and that was for PFOA. For PFBS, this pink one here is the best performer, and that's ion exchange resin PSR2+. So Fluorosorb did break through. It didn't break through as fast as some of the other the GACs, but it did break through. But it is less than their responsible level, which is in 500. I think it's 500 nanograms per liter. They also did RSSCTs. How am I doing on time? I can't see my clock right now. Just want to make sure. Okay,
you still got 5 minutes left.
5 minutes. Okay, good. Real quick on the RSSCT results, this is what an RSSCT column looks like. The bed volume is like about, it varies, but let's say it's about 2 milliliters. And you're able to run many different test conditions. So you can see, you can compare different waters and that sort of thing, and much quicker than doing a pilot study, which would take months. And so Orange County Water District compared a high DOC or dissolved organic carbon water, the levels are shown here, to a low organic carbon water, because organic carbon can, even small changes, small increases in dissolved organic carbon can increase the, or cause problems for GAC absorption of PFAS. And what they found was that Fluorosorb was not affected by the DOC concentration, and Fluorosorb was able to outperform the GAC in the high and the low DOC condition, but the high DOC condition, it was significant improvement. And this is specifically because GAC, other dissolved organic carbon compounds compete with PFAS for sorption on GAC, and that is not the case with Fluorosorb, which is specific. The surface modification is specific for PFAS. And so if you're okay with not absorbing dissolved organic carbon, then Fluorosorb is a great adsorbent for PFAS because the DOC just goes right through. And that's what this plot here shows. The C over C naught is a measure of the breakthrough, and the volume filtered is the volume that was treated before you hit your treatment target, which is 60% of the influent. This is for PFOA. And you can see that Fluorosorb took the longest to break through under the high DOC condition, and compared to GAC shown here, and so therefore more water was treated before you would have to change out your media in a vessel, for example. All right, moving on. I have one last set of results to show. This is treating landfill leachate, and this with RSSCTs, or this is lab studies with RSSCTs showing Fluorosorb absorption of PFAS from landfill leachate. And this was this is a setup here. These are the RSSCTs are scaled up using a constant diffusivity scaling to get an idea of what it would be like in a pilot study. This landfill leachate had a TOC of 560 milligrams per liter, so it's significantly higher concentration than most groundwaters. It's a high strength leachate. The conductivity is shown here is really high. There's a lot of anions and cations.
2 minutes remaining.
So the conclusion is that Fluorosorb was able to treat many more bed volumes for all different PFAS compounds than the comparison to GAC, and that was judged by 60% of the treatment to 60% of the influent concentration. And we have several full-scale landfill leachate systems that are going in specifically because Fluorosorb is not affected by the background or the other water quality constituents. I just want to make one comment about soil stabilization. Fluorosorb can be used to stabilize PFAS in soil. This plot is showing the reduction in leaching of a PFAS leaching from soil for a 5% mix of Fluorosorb organic and ordinary Portland cement. And you can see that it was able to reduce the leaching beneath they were using the EPA health advisory limit as compared to 0% Fluorosorb. And we also have a full-scale application for soil stabilization of PFAS with Fluorosorb. So conclusions, surface modified clay, the key things to remember, it has a high absorption capacity for a variety of PFAS and is specific for PFAS. The absorption kinetics are fast. You can use a 2-minute empty bed contact time if you're looking at drinking water filtration. It's resistant to competitive absorption by co-contaminants, and it's very versatile in its deployment. So I'd like to end there, and I'd be happy to take any questions.
Actually, we are right at time, so we don't have time
great.
for any questions.
Okay.